You know, in math, we just assume that two different points are, well, different. But what if they weren't? What if they were so close they were basically the same? Today, we're going to dive into the rules that give points some personal space. These are the topological separation axioms, and it all kicks off with one big question.
Right. How can we really guarantee, that two different points are truly separate? Because believe it or not, in some pretty strange mathematical spaces, two points can be so tangled up they're topologically indistinguishable. So the separation axioms? They're basically a set of rules we came up with to give these points some breathing room and make sure they're actually distinct.
All right, so here's our game plan. First, we'll tackle what I'm calling the separation problem. Then, we'll look at how we tell points apart. We'll hit the Hausdorff rule, which is a big one. After that, we'll move on to separating entire sets. And finally, we'll see how this all fits together in a kind of hierarchy of spaces.
Okay, let's get into it. The separation problem. So what if points were indistinguishable? Really think about that. Imagine a space where any little bubble you draw around point A, and in topology we call these bubbles open sets. Well, any bubble around A has to contain point B, and any bubble you draw around B has to contain A. They're just stuck together. It's a real mess, and it makes doing a lot of normal math pretty much impossible.
So how do we fix this? Well, the goal is to create some rules, or axioms if you want to be formal, that basically force points to be distinct and just behave themselves. You can think of these axioms as a series of upgrades you can install in a space to make it more structured, more predictable. We're basically going from total chaos to a nice, clean, orderly space, one rule at a time.
All right, Section 2, telling points apart. And for this, we're going to introduce our first two upgrades, T0 and T1 spaces.
Okay, so the T0 space, also known as a Kolmogorov space. This is the first rung on our ladder. The rule is pretty simple. For any two distinct points, you just have to find an open set, our bubble, that contains one of them but not the other. That's it. It's the absolute bare minimum for saying, hey, these two things aren't the same.
Let's use an analogy here. The T0 rule is like being able to put a bubble around at least one of 2 points to show it's different. So if you have points x and y, maybe you can find a bubble for x that avoids y, but you can't find one for y that avoids x. It's a one-way street, but hey, it's a start. It's our first real step out of that topological mess.
Then we level up to a T1 space, or a Fréchet space. Here, the rule gets a lot stronger. For any two distinct points, each of them has an open set containing it, but not the other. See the difference? It's not a one-way street anymore. Now, it's mutual. You can put a bubble around x that misses y, and you can put a bubble around y that misses x.
So let's just put them side by side. With T0, you're only guaranteed an open set for one of the points. But with T1, you're guaranteed an open set for each of them. That little change, from one to each, is a massive leap. T1 gives you this mutual, two-sided confirmation that, yep, these points are definitely separate. It's a huge step towards making our space much more well-behaved.
Okay, moving on to Section 3, the Hausdorff rule. And this, my friends, is the gold standard for separation. A lot of mathematicians would say this is where things get really interesting. This is the T2 space.
So what makes a Hausdorff space so special? Well, any two distinct points can be separated by, and this is the key, disjoint open sets. That little equation, U intersect V equals the empty set, means their bubbles don't overlap at all. It's not just that X has a bubble that misses Y. It's that X has a bubble and Y has its own bubble, and those two bubbles are guaranteed not to touch. They have their own personal space.
Yeah, I love this quote. The Hausdorff rule is like giving each point its own personal bubble that never touches anyone else's. And that's exactly it. This personal bubble property is absolutely crucial. It's the reason why fundamental ideas in calculus, like a sequence having a single unique limit, actually work. Without this rule, things fall apart. So yeah, it's a really, really big deal.
And you know what? This should actually feel pretty familiar. The good old real number line is a perfect example of a Hausdorff space. Just think about it. Pick any two different numbers, say 2 and 5. You can easily draw little bubbles or intervals around them that don't overlap at all, right? That's the Hausdorff property in action. And that's a huge reason why it behaves so predictably.
All right, section 4. We're leveling up. We've gotten pretty good at separating individual points. But what about separating a single point from a whole cluster of points? Or separating two entire clusters from each other? To do that, we have to introduce T3 and T4 spaces.
Okay, first up is a T3 space, which we also call a regular space. And the rule here is it has to be a T1 space, where you can separate any point from any disjoint closed set. Now, what's a closed set? Real simple. Think of our open bubble. A closed set is like that bubble plus its boundary. It's a solid region. So the T3 rule says you can take a point and a closed set that doesn't contain it, and you can put them in two separate, non-overlapping bubbles.
So the analogy is pretty straightforward, right? We can draw a bubble around a single point and a completely separate, bigger bubble around an entire closed-off region. We're not just separating 2 points anymore. We're putting a protective barrier between an individual and a whole community.
And that brings us to the T4, or normal space. This is kind of the ultimate level of separation we're going to talk about. It's a T1 space where you can take any two disjoint closed sets, two separate clusters, and separate them with open sets. You can put each entire cluster inside its own bubble, and those bubbles won't touch. And guess what? Every metric space, that's any space where you can actually measure distance, is a T4 space. That includes our trusty real number line, R. It meets this super high standard, which is a huge part of what makes it so rock solid and reliable for all sorts of math and science.
Okay, last section, a hierarchy of spaces. So we've just talked about a bunch of these axioms, from T0 all the way up to T4. So how do they all fit together? Well, it turns out they form this beautiful, clean hierarchy. You can think of it as a ladder of separation.
And here's the ladder. At the bottom, you've got T0, where at least one point is separable. Then T1, separating 2 points with individual sets. T2, the Hausdorff space, separates them with disjoint sets. T3 separates a point from a closed set. And at the very top, T4 separates 2 closed sets. The really cool part is that this is a strict hierarchy. Any space that's T4 is automatically T3 and T2 and so on. As you go up, you just get stronger and stronger guarantees.
So really, the higher you climb this ladder, the more structured and, well, nice the space becomes. Down at the T0 level, things can still be pretty wild. But as you climb, the spaces get more and more well-behaved, more predictable, and frankly, a lot easier to work with.
And that really brings us to the big takeaway. Our familiar number line is a T4 space. It's at the top of the ladder, it's the nicest of them all. And these rules, these separation axioms, are precisely why it's so reliable for everything from basic algebra to complex physics. That niceness is built right into its DNA.
So, that leaves us with a pretty wild thought, doesn't it? If these rules are what create the predictable, stable, mathematical worlds we rely on every day, what kind of bizarre possibilities are lurking in spaces that fail even the most basic of these rules? What do those worlds even look like? Something to think about. Thanks for tuning in.